Tonight, we're going to confront one of the deepest unsolved problems in all of science. There is a scale in the universe, a specific size so unimaginably small that something extraordinary happens there. Our two greatest theories of physics, the ones that describe everything from atoms to galaxies with stunning precision, stop making sense together. Individually, each theory is among the most successful ideas humans have ever produced. Quantum mechanics has never made a wrong prediction. General relativity has never made a wrong prediction. But when you push them both to this one scale, they contradict each other. They cannot both be right at the same time in the same place. This isn't a small technical disagreement, it's a fundamental clash built into the deepest structure of our understanding. And what it reveals about the nature of space, time, and reality itself is something most people have never heard. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference. Now, let's begin. There is something deeply wrong at the heart of physics. Not a small technical disagreement that a few clever equations could resolve. Not a minor inconsistency tucked away in some obscure corner of mathematics. Something fundamental, something so deep that it touches the very meaning of space and time. And it comes down to this. We have two theories, two frameworks for describing how the universe works. Each one has been tested more rigorously than almost anything else in science. Each one has survived every experiment ever thrown at it within its own domain. And they completely contradict each other. These are not fringe ideas. These are not speculative models or untested hypotheses. These are the two pillars upon which all of modern physics stands: quantum mechanics and general relativity. Together, they explain virtually every physical phenomenon we have ever observed, from the behavior of individual electrons to the expansion of the entire universe. Separately, each one is a masterpiece, a towering intellectual achievement that has reshaped our understanding of reality. But when you try to combine them, when you push them both into the same situation at the same scale, the mathematics does not just become difficult, it collapses entirely. You get infinities where you should get numbers. You get contradictions where you need consistency. You get predictions that are not merely wrong but physically meaningless. Some of the greatest minds in history have tried to fix this. Albert Einstein spent the last 3 decades of his life searching for a unified theory that would resolve the conflict. Richard Feynman, one of the most gifted physicists who ever lived, called the problem deeply disturbing. Stephen Hawking devoted much of his career to understanding what happens where these two theories collide, particularly inside black holes, where gravity is extreme and quantum effects cannot be ignored. Thousands of researchers across multiple generations have worked on this problem. Entire academic departments exist for it. And while we have made real progress, while we have candidate ideas and promising frameworks, we still do not have a complete resolution. The tension between quantum mechanics and general relativity remains one of the deepest unsolved problems in all of science. To understand why physics breaks, you first need to understand what each theory actually says, and why each one is so remarkably, almost absurdly, successful on its own. Quantum mechanics was born in the early 1900s, and it was born out of pure desperation. By the end of the 1800s, classical physics seemed nearly complete. Newton's laws described motion with exquisite precision. Maxwell's equations unified electricity, magnetism, and light into a single, elegant framework. Thermodynamics described heat, energy, and entropy. Together, these pillars explained an enormous range of phenomena: the motion of planets, the behavior of gases, the propagation of light, the properties of materials. Some prominent physicists even suggested there was nothing truly fundamental left to discover. The basic laws of nature were known. All that remained was refining the details and measuring constants to a few more decimal places. But cracks were appearing. Small, stubborn problems that refused to yield to classical reasoning. One of the most troubling was the behavior of hot, glowing objects. When you heat a piece of metal until it glows, it emits radiation across a range of frequencies. Classical physics predicted the amount of energy emitted at each frequency. But at high frequencies, the prediction went catastrophically wrong. The equations said the metal should emit infinite energy at ultraviolet and higher frequencies. This was called the ultraviolet catastrophe, and it was obviously absurd. Glowing metal does not release infinite energy. Nothing does. But classical equations insisted it should, and no one could figure out what was wrong. In 1900, a German physicist named Max Planck proposed something radical. He suggested that energy does not flow continuously, like water from a tap. Instead, energy comes in tiny, discrete packets, which he called quanta. Each quantum of energy is proportional to the frequency of the radiation. The constant linking them, now called Planck's constant, would become one of the most important numbers in all of physics. At the time, Planck viewed this as a mathematical fix, a trick to make the equations work. He was not entirely comfortable with the idea that energy actually comes in discrete chunks. But it solved the ultraviolet catastrophe perfectly. The numbers matched experiment with extraordinary precision. The mathematics demanded discreteness, even if Planck's intuition resisted it. 5 years later, Albert Einstein took the idea further. He proposed that light itself is not merely a continuous wave, as Maxwell's equations described. Light also comes in discrete packets, particles of light that we now call photons. Each photon carries a specific amount of energy, determined by its frequency. This explained a phenomenon called the photoelectric effect. When you shine light on certain metals, electrons are ejected from the surface. But there was something puzzling. The energy of the ejected electrons depended on the frequency of the light, not its brightness. Classical wave theory could not explain this at all. If light is a wave, brighter light should mean more energy, regardless of frequency. But experimentally, brightness did not matter. Only frequency did. Dim violet light could eject electrons while intense red light could not. Einstein's photon idea explained why immediately. Each photon is an individual packet of energy. If the frequency is too low, each individual photon simply does not carry enough energy to knock an electron loose, no matter how many photons you send, no matter how intense the beam is. Over the following 3 decades, quantum mechanics developed rapidly and became increasingly strange. Niels Bohr proposed a model of the atom in which electrons exist only in specific allowed energy levels, jumping between them in discrete leaps rather than smooth spirals. Werner Heisenberg formulated his uncertainty principle, revealing that you cannot simultaneously know both the exact position and exact momentum of a particle with perfect precision. This is not a limitation of our instruments. It is not a matter of needing better technology. The particle simply does not possess both properties simultaneously with definite values. Nature itself is fundamentally uncertain at the quantum scale. Erwin Schrödinger developed his wave equation, describing particles not as tiny billiard balls, but as spread-out wave functions representing probabilities of being found at different locations. And Paul Dirac combined quantum mechanics with Einstein's special relativity and predicted something nobody expected: the existence of antimatter, particles with the same mass as ordinary particles but opposite charge. Dirac predicted the positron, the antimatter counterpart of the electron, purely from the mathematics. It was discovered experimentally a few years later. The theory was telling us about particles that existed in nature before anyone had ever seen them. By the middle of the 20th century, quantum mechanics had matured into quantum field theory, a powerful framework that describes particles as excitations of fields pervading all of space. Every type of particle corresponds to a field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. And the forces between particles are described by the exchange of other particles. The electromagnetic force is carried by photons. The strong nuclear force, which holds the nuclei of atoms together, is carried by particles called gluons. The weak nuclear force, responsible for certain types of radioactive decay, is carried by particles called W and Z bosons. This framework, known as the Standard Model of Particle Physics, describes 3 of the 4 fundamental forces of nature and all known subatomic particles, and its precision borders on the absurd. Let me show you exactly how successful it is. Every electronic device you have ever used operates because of quantum mechanics. The transistor, the tiny switch at the heart of every computer chip, functions because of quantum mechanical properties of materials called semiconductors. When engineers design a modern processor containing billions of transistors, they use quantum mechanical equations to predict how electrons will behave in those tiny circuits. The fact that your phone works, that your computer processes billions of operations per second, that the internet exists as a global network, all of this is direct, practical confirmation that quantum mechanics correctly describes how matter behaves at the atomic scale. If quantum mechanics were even slightly wrong, none of this technology would function. Particle accelerators provide even more dramatic confirmation. The Large Hadron Collider at CERN, a ring of superconducting magnets 27 kilometers in circumference, buried beneath the border of France and Switzerland, smashes subatomic particles together at nearly the speed of light and measures what comes out with extraordinary precision. The Standard Model predicts the outcomes of these collisions. Consider the anomalous magnetic moment of the electron, a property describing how an electron responds to magnetic fields. Quantum electrodynamics, the quantum field theory of the electromagnetic force, predicts this quantity by summing up contributions from virtual particles briefly flickering in and out of existence around the electron. Experiments measure it. The two agree to better than 10 parts in a billion. This is often cited as the most precise agreement between theory and experiment in all of science. To put that in perspective, it is like predicting the distance from New York to Los Angeles and being accurate to within the thickness of a human hair. In 2012, the Higgs boson was discovered at the Large Hadron Collider, confirming a prediction that had been made nearly 50 years earlier. The particle's mass and its interactions with other particles matched the theoretical predictions of the Standard Model. Quantum field theory told physicists this particle should exist. It predicted how the particle should be produced, how it should decay, and how it should interact with other particles at any given mass, and the experiments confirmed it. Quantum mechanics explains why stars shine. Deep inside the core of the Sun, hydrogen nuclei are squeezed together under temperatures of about 15 million degrees and crushing pressure. But even under those extreme conditions, the electrical repulsion between protons should prevent them from ever getting close enough to fuse. Classical physics says it simply cannot happen. The energy barrier is too high. But quantum mechanics allows something remarkable. Through a process called quantum tunneling, particles have a small but non-zero probability of passing through energy barriers that classical physics says are impenetrable. This tunneling is what allows protons to fuse in the Sun's core. Without it, nuclear fusion would not occur. The Sun would not burn. No star in the universe would shine. Life as we know it would not exist. Quantum mechanics also explains why atoms are stable in the first place. In classical physics, an electron orbiting a nucleus should continuously radiate electromagnetic energy as it accelerates around its orbit. It should lose energy, spiral inward, and crash into the nucleus within a tiny fraction of a second. Every atom should collapse almost instantly. Matter as we know it should not exist. But quantum mechanics prevents this collapse. Electrons cannot spiral to any arbitrary energy. They exist in discrete energy levels, and there is a ground state, a lowest possible energy, below which an electron cannot fall. This is why atoms are stable. This is why solid matter holds together. This is why you do not pass through the chair you are sitting in right now. Lasers, magnetic resonance imaging machines, electron microscopes, atomic clocks, superconductors, light-emitting diodes, solar cells, all of these technologies are built directly on quantum mechanical principles. The theory does not merely describe the subatomic world in some vague or approximate way. It makes specific, quantitative predictions that match experiments to extraordinary precision. After well over a century of testing, quantum mechanics has never been shown to make a wrong prediction within its domain of applicability. Not once. It is arguably the most rigorously verified theory in all of human knowledge. Now let us turn to the other pillar. In 1915, Albert Einstein published his general theory of relativity, and it fundamentally transformed our understanding of gravity, space, and time. Before Einstein, gravity was understood through Isaac Newton's law of universal gravitation, published in 1687. Newton described gravity as a force. Every object with mass attracts every other object with mass. The strength of the force depends on the two masses involved and the distance between them. And this framework is extraordinarily successful. It predicts the orbits of planets around the Sun with high accuracy. It describes the trajectories of spacecraft as they travel through the solar system. It explains the ocean tides. It accounts for the motion of moons around their parent planets. Newton's gravity was so successful that it dominated physics for over 200 years and remains accurate enough for the vast majority of practical applications today. When NASA sends a spacecraft to Mars, Newton's equations are still used for most of the trajectory calculations. They work. But Newton himself recognized a deep and troubling problem with his own theory. In his framework, gravity acts instantaneously across any distance. If the Sun were to suddenly vanish, Newton's equations say Earth would immediately feel the loss of the Sun's gravitational pull and fly off in a straight line. The effect would be felt across 93 million miles of vacuum with zero delay. No signal, no transmission, just immediate action at a distance. Newton found this deeply unsatisfying. He openly admitted he could not explain the mechanism by which gravity acted across empty space, and wrote that the idea of one body acting on another through a vacuum without any intermediary was, to him, a great absurdity. Einstein resolved this by completely reimagining what gravity is. In Newton's picture, gravity is a force that acts between objects through empty space. In Einstein's picture, gravity is not a force at all. It is the curvature of space-time. Mass and energy warp the fabric of space-time around them, bending its geometry, and objects then move along the straightest possible paths through that curved geometry. The Earth does not orbit the Sun because a mysterious, invisible force pulls on it across 93 million miles. The Earth orbits because the Sun's enormous mass warps the space-time in its vicinity, creating a curved geometry, and the Earth follows the natural contours of that warped space-time. What we perceive and experience as the force of gravity is really the geometry of space-time guiding the motion of matter. This is not a poetic metaphor or a loose analogy. It is a precise mathematical framework. Einstein's field equations relate the distribution of mass and energy throughout the universe to the curvature of spacetime with rigorous mathematical exactness. They are among the most difficult equations in all of physics to solve, but when you do solve them, the predictions match observations with stunning accuracy. The orbit of Mercury provided the first great confirmation. Astronomers had known for decades that Mercury's orbit does not behave exactly as Newton's laws predict. The point where Mercury makes its closest approach to the Sun shifts slightly with each orbit, a phenomenon called the precession of the perihelion. Most of this precession is caused by the gravitational pull of other planets. But after accounting for all known influences, a tiny residual precession of about 43 arcseconds per century remained unexplained. Newton's theory could not account for it. General relativity predicted this residual precession exactly. When Einstein first calculated it and the numbers matched, the emotional impact was profound. He later said his heart had palpitations. He knew his theory was right. General relativity predicts that light bends as it passes through curved spacetime near massive objects. A beam of starlight grazing past the Sun should be deflected by a specific, calculable amount. In 1919, during a total solar eclipse that blocked the Sun's glare and made nearby stars visible, astronomers, led by Arthur Eddington, measured the positions of stars appearing close to the Sun and confirmed the deflection matched Einstein's prediction. This result made headlines across the world and transformed Einstein from a figure known mainly within the scientific community into an international celebrity practically overnight. General relativity predicts that time itself runs differently depending on the strength of the gravitational field. A clock sitting in a stronger gravitational field ticks more slowly than a clock in a weaker field. This is not a mechanical effect on the clock. It is not that the clock's gears are strained or its electronics are affected. Time itself genuinely passes at different rates in different gravitational environments. This has been measured directly and repeatedly with atomic clocks placed at different altitudes. And it has deeply practical consequences. The satellites that make up the global positioning system orbit Earth at an altitude where gravity is weaker than at the surface. The atomic clocks on those satellites tick at a slightly different rate than identical clocks on the ground. If this difference were not corrected using general relativity, GPS would accumulate errors of several kilometers within a single day. Your navigation would be useless. Every time you use GPS to find a restaurant or navigate to a new city, you are relying on general relativity being correct. In 2015, the LIGO observatories detected gravitational waves for the first time. These are ripples in the fabric of space-time itself, produced when two massive black holes spiraled toward each other and merged roughly 1.3 billion light-years away. The collision was violent beyond comprehension. In the final fraction of a second before merger, the two black holes were orbiting each other at nearly half the speed of light. The energy released in gravitational waves during that brief moment was greater than the combined light output of every star in the observable universe. The ripple travelled outward at the speed of light for over 1 billion years and finally reached Earth, stretching and compressing space by a distance roughly 1,000th the width of a proton, and LIGO detected it. The measured signal matched general relativity's predictions with remarkable precision. The shape of the waveform, the way the frequency increased as the black holes spiraled closer, the sudden ring down as the merged black hole settled into its final state, all of it followed what Einstein's equations had foretold a century earlier. General relativity describes the expansion of the universe itself. Einstein's field equations allow for solutions where the fabric of space stretches over time, carrying galaxies apart. This was confirmed observationally in 1929, when Edwin Hubble showed that distant galaxies are receding from us, and the farther away they are, the faster they recede. The entire framework of modern cosmology, the Big Bang, the cosmic microwave background, the formation of galaxy clusters across billions of light years, all of it rests on general relativity. And it works. Predictions match observations across cosmic scales. General relativity predicts black holes, regions of spacetime so severely curved that nothing, not even light, can escape once it crosses the boundary, called the event horizon. In 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow in the galaxy M87. The shape and size of the shadow matched general relativity's predictions. So here is where we stand. Two theories, quantum mechanics and general relativity. Each one has been tested to extraordinary precision over many decades. Each one is confirmed by vast mountains of experimental evidence. Each one is used in practical technology that you rely on every single day. If you ranked theories purely by how rigorously they have been tested and how precisely their predictions have been confirmed, these two would occupy the top of the list. Nothing else in all of science comes close to their track record. And they are fundamentally incompatible. This is not a minor disagreement about some obscure technical detail. The two theories describe reality in fundamentally different languages. They make contradictory assumptions about what the universe is at the deepest level. In quantum mechanics, space-time is a fixed, rigid background, a stage on which the drama of particles and forces plays out. The particles are dynamic. They fluctuate, they exist in superposition, they tunnel through barriers, they entangle across vast distances. But the stage itself, the space-time on which all this happens, is static and unchanging. Quantum mechanics does not describe space-time. It takes space-time as a given, as an unchangeable backdrop, and describes the physics that unfolds within it. In general relativity, the picture is reversed entirely. Space-time is not a passive background at all. It is dynamic. It bends and stretches and warps and ripples in response to the matter and energy it contains. And that bending, in turn, affects how matter moves. Space-time is not the stage, it is one of the performers. Matter tells space-time how to curve, and curved space-time tells matter how to move. This interplay between geometry and matter is the very essence of gravity, as Einstein described it. These two pictures are not merely different ways of saying the same thing, they are contradictory. Quantum mechanics says the stage is fixed and absolute. General relativity says the stage is dynamic and responsive. Quantum mechanics describes wildly fluctuating particles living on a perfectly smooth, unchanging spacetime. General relativity describes a spacetime that itself fluctuates and deforms in response to energy and matter. If you try to build a single consistent framework that respects both of these ideas, that applies quantum rules to a dynamic spacetime, the mathematics does not cooperate. The equations produce infinities that cannot be removed. The predictions become nonsensical. In most practical situations, this conflict stays safely hidden because the domains of the two theories barely overlap. When you study atoms and subatomic particles, gravity is so incredibly weak at those scales that it makes no measurable difference at all. The gravitational attraction between an electron and a proton inside a hydrogen atom is so incomprehensibly feeble compared to the electromagnetic force holding them together that it might as well be zero. You could ignore gravity entirely and lose nothing. Quantum mechanics works perfectly without it. When you study planets, stars, or galaxies, quantum effects are so negligible at those scales that they make no measurable difference. A planet does not exhibit quantum superposition. Its position and momentum are defined with far more precision than the quantum limit would constrain. General relativity works perfectly without any reference to quantum mechanics. Each theory dominates its own territory, and the two territories barely touch. But there is a regime where they must overlap. A specific scale where quantum effects and gravitational effects both become equally important at the same time in the same place. A scale where ignoring either one is simply not possible. A scale where both theories demand to be applied simultaneously. And when you try to apply both theories simultaneously, forcing them into the same equations at the same scale, the mathematics falls apart entirely. You do not get a slightly wrong answer. You do not get an answer that is off by a small correction factor. You get meaningless infinities. The framework stops producing physical predictions altogether. This scale is not arbitrary. It is not something physicists selected for convenience. It emerges inevitably from the fundamental constants of nature themselves, from the very numbers woven into the deepest structure of physical law. It marks the boundary where our understanding of physics reaches its most fundamental limit. It is called the Planck scale, and what happens there, why it arises, and why it represents something far more profound than simply being very, very small, is what we need to understand next. The Planck scale is not just another small distance. It is not simply the next step down in a progression from atoms to nuclei to quarks to whatever lies beneath. It is fundamentally different from every other scale in physics, and understanding why requires understanding where it comes from. Because the Planck scale is not something physicists invented or chose, it was not selected as a convenient benchmark. It emerges on its own, inevitably, from the deepest constants woven into the structure of reality. And that is what makes it so extraordinary. To understand how the Planck scale arises, you need to understand three numbers. Three constants that appear over and over again in the fundamental laws of nature. Each one anchors one of the great pillars of physics. Each one describes something essential about how the universe works. And when you combine them, when you take these three numbers and ask what length, what time, what energy scale naturally emerges from all three operating simultaneously, you get the Planck scale. You do not need to assume anything. You do not need to guess. The mathematics gives you a single, unique answer. Let me walk you through each one. The first constant is the speed of light. It is approximately 299,792 kilometers per second. For simplicity, we usually round this to 300,000 kilometers per second. This is not merely the speed at which light happens to travel. It is a fundamental property of space-time itself. It is the maximum speed at which any information, any signal, any causal influence of any kind can propagate through the universe. Nothing with mass can reach it. Nothing without mass can avoid it. Photons, the particles of light, must travel at exactly this speed. They cannot go faster, and they cannot go slower. The speed of light connects space and time. Before Einstein, space and time were considered separate, unrelated things. Space was a three-dimensional arena where things existed. Time was a separate, universal clock that ticked at the same rate everywhere for everyone. Einstein showed this is wrong. Space and time are woven together into a single four-dimensional fabric called spacetime, and the speed of light is the conversion factor between them. It tells you how much space is equivalent to how much time. When you travel through space, you travel less through time. When you stand still in space, you travel through time at the maximum possible rate. The speed of light governs this exchange. It is the fundamental constant of Einstein's special and general theories of relativity. Wherever relativity matters, the speed of light is there. The second constant is the gravitational constant. It is approximately 6.67 times 10 to the negative 11 in standard units. This number tells you how strong gravity is. It appears in Newton's law of universal gravitation, and it appears in Einstein's field equations of general relativity. The gravitational constant sets the scale of the gravitational interaction. It determines how much spacetime curves in response to a given amount of mass or energy. If the gravitational constant were larger, gravity would be stronger. Stars would burn faster and hotter. Planets would weigh more. Black holes would form more easily. If the gravitational constant were smaller, gravity would be weaker. Stars might not ignite at all. Galaxies might never have formed. The universe would be a completely different place. Here is something important about gravity. It is absurdly weak compared to the other fundamental forces. The electromagnetic force between two charged particles is roughly 10 to the 36th power times stronger than the gravitational force between those same particles. Think about what that means. When you pick up a paperclip with a small refrigerator magnet, the electromagnetic force in that tiny magnet is overcoming the gravitational pull of the entire planet Earth. Every atom in the entire Earth is pulling that paperclip downward, and a magnet the size of your thumbnail overpowers all of it. That is how weak gravity is compared to electromagnetism. This weakness is why gravity is irrelevant in quantum mechanics under ordinary conditions. When you study the behavior of atoms, electrons, and subatomic particles, the gravitational force between them is so fantastically small that it makes no difference whatsoever. You could remove gravity entirely from your equations, and your predictions about atomic and subatomic physics would not change by any measurable amount. This is why quantum mechanics was developed without including gravity. It was not needed. The other forces dominate so overwhelmingly at small scales that gravity might as well not exist. But this changes at extreme energies and extreme densities. At the Planck scale, gravity can no longer be ignored, and that is precisely where the trouble begins. The third constant is Planck's constant, specifically the reduced form called h bar. It is approximately 1.05 times 10 to the negative 34 in standard units. This is the signature of quantum mechanics. It appears everywhere that quantum effects matter. It is in the uncertainty principle, which says the uncertainty in a particle's position multiplied by the uncertainty in its momentum must always be at least as large as h bar divided by 2. It is in the energy of a photon, which is proportional to its frequency, with h bar providing the conversion. It is in Schrödinger's equation, the master equation governing how quantum systems evolve over time. Wherever the universe behaves in a fundamentally quantum way, wherever energy comes in discrete packets, wherever uncertainty is unavoidable, wherever particles behave like waves, Planck's constant is there, setting the scale. Planck's constant is incredibly small in everyday units. This is why quantum effects are invisible in daily life. At human scales, Planck's constant is so tiny relative to the energies and momenta of objects we interact with that the quantum fuzziness it introduces is completely undetectable. A thrown baseball has a quantum wavelength so absurdly small that you would need a number with over 30 digits just to write it down. The ball behaves exactly like a classical object for all practical purposes. But at atomic scales, where energies and momenta are small, Planck's constant becomes significant. Electrons in atoms have wavelengths comparable to the size of the atom itself. Quantum effects dominate. The universe becomes fundamentally probabilistic, discrete, and strange. So these are the three constants. The speed of light anchors relativity. The gravitational constant anchors gravity. Planck's constant anchors quantum mechanics. Each one governs a different aspect of physics. Each one sets the scale at which its corresponding theory becomes essential. Now here is the key insight. These three constants have different physical dimensions. The speed of light has dimensions of length divided by time. The gravitational constant has dimensions of length cubed divided by mass times time squared. Planck's constant has dimensions of mass times length squared divided by time. They are all different, but if you combine them in the right way, you can construct quantities with the dimensions of length, time, mass, energy, and temperature. There is exactly one way to do this for each quantity. The mathematics is unique. There is no freedom in the choice. You simply ask what combination of these three constants gives you a length, and the answer is determined completely. The Planck length is the square root of h bar times the gravitational constant divided by the speed of light cubed. When you plug in the actual numerical values of these constants, the answer comes out to approximately 1.6 times 10 to the negative 35 meters. To appreciate how small this is, let me try to build a bridge between this number and something you can relate to. A human being is roughly 1.5 to 2 meters tall. An ant is about 1 millimeter, roughly 1,000th of your height. A human cell is roughly 10 micrometers, about 100th the size of that ant. A bacterium is roughly 1 micrometer, 10 times smaller than a cell. A virus is roughly 100 nanometers, 10 times smaller than a bacterium. A large molecule like DNA is roughly 2 nanometers wide. An atom is roughly 1/10 of a nanometer, about 1/10 billionth of a meter. The nucleus of an atom is roughly 1 femtometer, about 100,000th the size of the atom itself. A quark, as far as we can measure, is smaller than about 1,000th of a femtometer. And the Planck length is still roughly 17 orders of magnitude smaller than that. 17 orders of magnitude. That means if you could somehow shrink yourself down to the size of a quark, and then repeated that same shrinking process about 17 more times, each time reducing your size by a factor of 10, you would only then approach the Planck scale. The gap between our everyday experience and the Planck length is so vast that no analogy fully captures it. But there is one comparison that comes close to conveying the enormity. If you could take a single grain of sand, roughly 0.5 millimeter across, and inflate it until it was the size of the entire observable universe, 93 billion light-years in diameter, the Planck length, scaled up by that same factor, would be roughly the size of a grain of sand. The ratio between the Planck length and a grain of sand is approximately the same as the ratio between a grain of sand and the entire observable universe. Those two enormous jumps in scale, from the Planck length up to a grain of sand, and from a grain of sand up to the observable universe, are roughly equal. That is how small the Planck length is. Similarly, the Planck time is approximately 5.4 times 10 to the negative 44 seconds. This is the time it takes light, the fastest thing in the universe, to cross one Planck length. It is the shortest interval of time that has any clear physical meaning within our current theories. The Planck mass is approximately 2.2 times 10 to the negative 8 kilograms. That is roughly the mass of a small flea egg or a grain of fine dust. This might surprise you. After all, the Planck length and Planck time are unimaginably small. You might expect the Planck mass to be tiny too, but it is not. By the standards of particle physics, the Planck mass is enormous. A proton has a mass of roughly 1.7 times 10 to the negative 27 kilograms. The Planck mass is roughly 10 to the 19th power times larger. That is 10 billion times the mass of a proton concentrated at a single point. This enormous energy concentrated at the Planck scale is exactly what creates the problem. The Planck energy, the energy equivalent of the Planck mass through Einstein's famous E equals mc squared, is approximately 2 times 10 to the 9th joules. That is roughly the energy released by burning 50 litres of gasoline. Again, this is enormous by particle physics standards. The most powerful particle accelerator ever built, the Large Hadron Collider, accelerates protons to energies of roughly 10 to the negative 6 joules. The Planck energy is about 10 to the 15 power times larger than what the Large Hadron Collider achieves. To reach Planck energy with a particle accelerator using current technology, you would need an accelerator roughly the size of the Milky Way galaxy. This is not a practical challenge that better engineering could solve. It is a fundamental gap of 15 orders of magnitude between what we can do and what we would need to do. The Planck temperature is approximately 1.4 times 10 to the 32 degrees Kelvin. This is the temperature at which the average thermal energy of particles equals the Planck energy. Nothing in the universe today is anywhere close to this temperature. The hottest known objects in the present universe, the cores of the most massive stars just before they explode as supernovae, reach temperatures of roughly 100 billion degrees. The Planck temperature is roughly 10 to the 21st power times hotter than that. Now, the existence of these values alone is interesting, but what makes the Planck scale truly significant is not the smallness of the numbers. It is the physical meaning behind them. The Planck scale is not merely a very small distance. It is the specific distance at which quantum effects and gravitational effects become equally important simultaneously. And this is something that does not happen at any other scale. Let me explain exactly why. In quantum mechanics, there is a deep connection between the size of something you want to observe and the energy you need to observe it. This follows directly from the uncertainty principle. To probe smaller and smaller distances, to resolve finer and finer details of the structure of matter, you need probes with shorter and shorter wavelengths. And shorter wavelengths mean higher energies. This is why electron microscopes see smaller things than optical microscopes. Electrons can have much shorter wavelengths than visible light. This is why particle accelerators use incredibly high energy collisions. The higher the energy, the shorter the effective wavelength, and the smaller the structures you can resolve. This relationship is fundamental and inescapable. If you want to study something at the scale of an atom, you need probe energies on the order of electron volts. If you want to study something at the scale of a nucleus, you need energies of millions of electron volts. If you want to study quarks inside a proton, you need energies of billions of electron volts. There is no way around this. The uncertainty principle demands it. Smaller distances require higher energies. Now, here is where gravity enters the picture in a way that changes everything. In general relativity, energy curves spacetime. Mass and energy are equivalent, and both create gravitational fields. The more energy you concentrate in a small region, the more you curve the spacetime around that region. At everyday energies, this curvature is negligible. The gravitational field created by a single subatomic particle is so fantastically weak that it has no measurable effect on anything. This is why quantum mechanics can safely ignore gravity. The energies involved in atomic and subatomic physics are far too small to curve spacetime in any meaningful way. But as you probe smaller and smaller distances, the energies required grow larger and larger. And as the energies grow, the gravitational effects of those energies become more significant. At some point, as you push to smaller and smaller scales, the energy you need to concentrate in a small region becomes so enormous that the gravitational curvature it produces is no longer negligible. It becomes significant. It becomes dominant. There is a specific threshold where something dramatic happens. The energy you would need to probe a certain distance becomes so large that when concentrated in that region, it would curve spacetime so severely that a black hole forms. This is the physical core of the problem. A black hole is a region of spacetime curved so extremely that nothing can escape it. Once you form a black hole in the region you are trying to study, you cannot extract any information from inside it. The event horizon, the boundary of the black hole, prevents any signal from getting out. The very act of trying to measure the distance has destroyed your ability to measure it. The probe has created a gravitational barrier that conceals whatever you are trying to observe. And the size of a black hole grows with its energy. A more energetic probe creates a larger black hole. So if you try to use even more energy to punch through, to probe even smaller distances, the black hole you create is not smaller. It is larger. The harder you push, the worse it gets. You are caught in an inescapable trap. Below a certain distance scale, any attempt at measurement creates a black hole that is bigger than the distance you are trying to resolve. The measurement defeats itself. That critical distance is the Planck length. It is the scale at which the quantum mechanical wavelength of your probe equals the Schwarzschild radius of a black hole with the same energy. Below this scale, probing becomes self-defeating. You cannot localize anything more precisely than the Planck length, because doing so requires enough energy to form a black hole that swallows the very region you are examining. This is not a technological limitation. It is not a matter of needing better instruments, or smarter experimental techniques, or more funding. It is a consequence of the fundamental laws themselves. Quantum mechanics demands that smaller distances require higher energies. General relativity demands that higher energies in small regions create stronger gravitational fields. At the Planck scale, these two demands collide head-on and create an absolute barrier. No experiment, no matter how cleverly designed, not even in principle, can measure distances smaller than the Planck length. Not because we lack the technology, but because the laws of physics as we currently understand them say the concept of distance smaller than the Planck length may not be meaningful. Let me put this differently to make sure the physical picture is clear. Imagine you are trying to take a photograph of something incredibly tiny. To get a sharp image, you need light with a wavelength smaller than the object you are photographing. If you want to photograph something 1 nanometer across, you need light with a wavelength shorter than 1 nanometer. This is the same principle behind using electron microscopes instead of optical microscopes for very small structures. Now imagine you are trying to photograph something at the Planck scale. You would need a probe with a wavelength of about 10 to the negative 35 meters. The energy required for such a probe would be the Planck energy, roughly the energy of burning 50 liters of gasoline concentrated into a single subatomic particle. When that much energy is focused into a Planck-sized region, general relativity tells you the space-time in that region curves so severely that it collapses into a black hole. The flash of your camera, so to speak, creates a black hole that swallows the subject of your photograph. You cannot see anything because you have just sealed it behind an event horizon. And if you try using an even more powerful flash, concentrating even more energy to get a sharper image, the black hole you create is even larger. Your photograph is now blurred, not because your camera is too weak, but because your camera is too strong. Every increase in resolution makes the situation worse. There is a sweet spot, the Planck scale, where the trade-off is balanced. Sharper than that is impossible because gravity takes over and destroys the measurement. This is why the Planck scale is not just very small. This is why it represents something categorically different from atomic scales or nuclear scales or quark scales. At all those other scales, you can, in principle, improve your measurement by using more energy, better instruments, cleverer techniques. The challenge is practical, not fundamental. But at the Planck scale, the challenge is fundamental. The laws of quantum mechanics and the laws of general relativity together create an absolute flaw beneath which the concept of spatial resolution loses its meaning. Think about what this implies. Throughout the history of physics, we have always been able to probe deeper. We looked inside matter and found molecules. We looked inside molecules and found atoms. We looked inside atoms and found nuclei and electrons. We looked inside nuclei and found protons and neutrons. We looked inside protons and neutrons and found quarks and gluons. At every stage, the smaller scale was there, waiting to be discovered. All we needed was more energy, more precision, better tools. The universe always had another layer beneath. The Planck scale suggests this may not continue forever. There may be a bottom. Not because the universe runs out of structure, but because the very concepts of distance and structure may not apply below this scale. This has profound implications for what spacetime itself might be. In general relativity, spacetime is smooth and continuous. You can divide any distance in half, and half again, and half again, forever. Between any 2 points, no matter how close, there are infinitely many other points. Space is a perfect, smooth continuum, infinitely divisible, with no granularity, no gaps, no smallest unit. But if the Planck length represents a true minimum meaningful distance, then this picture of smooth, continuous spacetime must be an approximation. It might be an extraordinarily good approximation at the scales we can probe today, just as treating water as a smooth fluid is an excellent approximation, even though it is actually made of discrete molecules. But at the Planck scale, the granularity would become apparent. Spacetime might not be smooth at all. It might have some kind of discrete structure, a fundamental graininess that only becomes evident at the smallest conceivable scale. The Planck time has a similar significance. If the Planck length is the smallest meaningful distance, the Planck time is the smallest meaningful duration. Events separated by less than 1 Planck time might not have a well-defined temporal ordering. The notion of before and after might blur at this timescale, just as the notion of here and there might blur at the Planck length. Time, as we understand it, a smooth, continuous progression from past to future, might be an approximation that breaks down at the most fundamental level. And the Planck energy tells you the cost of accessing this regime. To directly probe the Planck scale experimentally, you would need to concentrate the Planck energy into a Planck-sized region. That energy, roughly equivalent to burning 50 litres of gasoline, does not sound impressive in everyday terms. But concentrating that energy into a volume 10 to the negative 35 meters across is beyond anything remotely achievable. It exceeds the capability of the most powerful particle accelerator ever built by 15 orders of magnitude. There is no realistic prospect of building an accelerator that could reach Planck energies directly. The engineering requirements would be absurd. The accelerator would need to be roughly the size of a galaxy. This is one of the great frustrations of Planck scale physics. We know something extraordinary happens there. We know our theories conflict there. We know that resolving the conflict would reveal deep truths about the nature of space, time, and reality. But we cannot directly probe this scale experimentally. The Planck scale is a place we can reason about, a place we can explore mathematically, a place we can study through indirect observational consequences. But it is not a place we can examine directly with any instrument we can currently conceive of building. Yet the Planck scale is not merely a theoretical curiosity. It is physically real. There was a time in the history of the universe when the Planck scale was not hidden deep beneath layers of larger structure. In the earliest moments after the Big Bang, when the universe was less than 1 Planck time old, the entire observable universe was compressed to a size smaller than 1 Planck length. The temperature was above the Planck temperature. The energy density exceeded the Planck density. At that moment, there was nowhere to hide from the conflict between quantum mechanics and gravity. Both were essential. Both were operating at full strength, and our current theories cannot describe what happened. The first Planck time of the universe remains a complete mystery. We have detailed models of what happened from roughly 10 to the negative 43 seconds onward. We can trace the expansion of the universe, the cooling of the primordial plasma, the formation of the first protons and neutrons, the creation of light nuclei during the first few minutes, the release of the cosmic microwave background radiation roughly 380,000 years later, the gradual formation of stars and galaxies over billions of years. The history of the universe from that point forward is remarkably well understood and confirmed by extensive observational evidence. But the first Planck time remains blank. We cannot calculate what happened because we do not have a theory capable of handling it. General relativity alone predicts a singularity, a point of infinite density and infinite curvature, which is not a physical prediction, but a sign that the theory has exceeded its limits. Quantum mechanics alone does not include gravity and cannot describe the extreme gravitational conditions of the primordial universe. We need both. We need a theory that is simultaneously quantum mechanical and gravitational, and we do not yet have one that is complete and experimentally confirmed. Inside black holes, the same problem arises. General relativity
predicts that the matter collapsing to form a black hole compresses to a singularity at the center, an infinitely dense point where curvature becomes infinite. But infinite density means the matter is compressed into a region far smaller than the Planck length. At that point, quantum effects must be enormous. You cannot have a region smaller than the Planck length with the mass of a star in it and ignore quantum mechanics. The singularity is not a real physical prediction. It is a signal that general relativity has been pushed beyond its domain of validity. Something else happens at the center of a black hole, something governed by physics we do not yet fully understand. The Planck scale is where the universe keeps its deepest secrets. It is the threshold below which our most powerful theories cease to function together. It is the floor beneath which the very fabric of spacetime may break apart into something we do not yet have the language to describe. And it is not an arbitrary boundary drawn by human convention. It is etched into the constants of nature themselves, emerging inevitably from the speed of light, the strength of gravity, and the scale of quantum effects. Every theory of quantum gravity, every serious attempt to unify quantum mechanics with general relativity, confronts the Planck scale as its central arena. Whatever the correct theory turns out to be, it must operate naturally at this scale. It must explain what happens when quantum effects and gravitational effects are both operating at full strength in the same region at the same time. It must replace the infinities and contradictions of our current theories with finite, meaningful, and testable predictions. And it must do so in a way that reproduces the spectacular successes of both quantum mechanics and general relativity in the regimes where each one works so beautifully on its own. That is the challenge. And to understand why it is so difficult, to understand the specific ways in which our theories shatter when forced together at this scale, we need to look more closely at what actually goes wrong.
Because the problems are not vague or abstract. They are precise, mathematical, and deeply revealing about what our theories are missing. When physicists say that quantum mechanics and general relativity are incompatible, they are not speaking loosely. They are not using incompatible as a vague term, meaning the two theories feel different or approach reality from different philosophical angles. The incompatibility is precise, mathematical, and devastating. When you attempt to apply the standard tools of quantum theory to gravity, specific things go wrong in specific ways. The equations do not merely become difficult, they produce results that are physically meaningless. Understanding exactly how they break is essential to understanding why the Planck scale matters and why finding a resolution is one of the most important challenges in all of science. Let me start with the problem that physicists call non-renormalizability, because it is the most direct and technically concrete way that gravity resists being made quantum mechanical. In quantum field theory, the framework underlying the standard model, forces between particles are described by the exchange of other particles. Two electrons repel each other because they exchange virtual photons. Two quarks attract each other because they exchange virtual gluons. The weak nuclear force operates through the exchange of W and Z bosons. In each case, the force-carrying particle mediates the interaction. You can visualize these interactions using diagrams invented by Richard Feynman. A Feynman diagram shows particles coming in interacting by exchanging force carriers and going out. The simplest diagrams involve just one exchange. One photon bouncing between two electrons, one gluon bouncing between two quarks. These simple diagrams give you an approximate answer for the strength of the interaction. But quantum mechanics demands that you also consider more complicated diagrams. What if the exchanged photon briefly splits into a virtual electron and a virtual positron before recombining? What if those virtual particles themselves emit and absorb additional virtual photons? What if those additional photons produce their own virtual pairs? Every possible sequence of virtual processes contributes to the final answer. Quantum mechanics says you must sum over all of them. When you begin adding up these contributions, a problem appears. Many of the more complicated diagrams involve virtual particles with very high energies, and when you integrate over all possible energies these virtual particles can have, the integrals diverge. They go to infinity. The sum of all diagrams gives you an infinite answer, which is obviously wrong. No physical quantity measured in a laboratory is infinite. Forces have finite strengths. Particles have finite masses. Something must be done about these infinities. The solution, developed in the late 1940s by Feynman, Julian Schwinger, and Shinichiro Tominaga, is called renormalization. The idea is subtle but powerful. You recognize that certain quantities in your theory, like the mass and charge of the electron, are not directly observable in their bare form. What you actually measure in experiments are effective values that already include the effects of all those virtual processes. The bare values are infinite, but the corrections from virtual particles are also infinite, and the two infinities can be arranged to cancel, leaving finite, measurable results. You absorb the infinities into a redefinition of the physical parameters of the theory. After renormalization, every prediction the theory makes is finite and meaningful. This sounds like a trick, and in a sense it is. But it is a trick that works spectacularly well. Quantum electrodynamics, the quantum field theory of the electromagnetic force, often abbreviated QED, was the first theory to be renormalized successfully. After renormalization, QED became staggeringly precise. It predicted the precise magnetic properties of the electron, the exact lifetimes of unstable particles, and the probabilities of every type of particle interaction in accelerator collisions, all confirmed by experiment to extraordinary accuracy. Renormalization transforms a theory plagued by infinities into one of extraordinary predictive power. The same technique works for the weak nuclear force and the strong nuclear force. The electroweak theory, which unifies electromagnetism with the weak force, is renormalizable. Quantum chromodynamics, or QCD, the theory of the strong force, is renormalizable. For all three of the non-gravitational forces, renormalization tames the infinities and produces a framework that makes finite, testable, and extraordinarily accurate predictions. The procedure is not arbitrary. There are strict mathematical conditions a theory must satisfy to be renormalizable. The three forces in the standard model satisfy those conditions. Gravity does not. When you try to construct a quantum field theory of gravity following the same recipe, you immediately encounter a catastrophic problem. In this approach, the gravitational force would be mediated by a particle called the graviton, just as the electromagnetic force is mediated by the photon.
The graviton would be a massless particle with a specific quantum mechanical property called spin 2. The theory seems to start off reasonably enough. You can write down the simplest Feynman diagrams, the ones involving just a single graviton exchange, and they give sensible answers. At this lowest level of approximation, quantum gravity looks similar to the other quantum field theories. But when you include the more complicated diagrams, the ones involving virtual gravitons producing more virtual gravitons in loops, the infinities that appear are of a completely different character than those in QED or QCD. In QED, there are only a few types of infinities, and they can all be absorbed into a few physical parameters like the electron's mass and charge. After that absorption, every prediction is finite. In quantum gravity, each level of complexity introduces new types of infinities that require new parameters to absorb them. At one loop of virtual gravitons, you need certain parameters. At two loops, you need additional parameters that were not needed before. At three loops, still more. At every successive level of approximation, new infinities appear that cannot be absorbed into previously existing parameters. The theory demands an infinite number of free parameters, and a theory with an infinite number of free parameters predicts nothing. To make any prediction, you would first need to measure infinitely many quantities and feed them in by hand. The theory does not constrain them. It does not tell you what they should be. Each one must be determined by experiment, but you cannot perform infinitely many experiments, so the theory has no predictive power. It is not that the calculations are hard, it is that the framework itself, the entire approach of applying standard quantum field theory techniques to gravity, does not work. The infinities win. They cannot be tamed by renormalization. Gravity is non-renormalizable. This is not a minor technical obstacle. It is a fundamental statement that the standard tools of quantum field theory, the tools that work beautifully for electromagnetism, the weak force, and the strong force, are the wrong tools for gravity. Something about gravity is fundamentally different from the other forces at the quantum level, and this difference is deeply connected to what gravity actually is. The other forces are forces in the conventional sense. They are interactions between particles that take place on a fixed background of spacetime. Electromagnetism acts on charged particles moving through space. The strong force acts on quarks moving through space. The background spacetime is there, fixed and unchanging, providing the stage. The forces are the actors, but gravity is not an actor on the stage. Gravity is the stage. General relativity tells us that gravity is the curvature of space-time itself. When you try to quantize gravity, you are not quantizing just another force that operates on a background. You are quantizing the background. You are trying to apply quantum rules to the very arena in which all other quantum physics takes place. This is a fundamentally different kind of problem. The stage itself becomes a quantum object, fluctuating, uncertain, probabilistic. And since every other theory assumes a fixed stage to define its calculations, removing that assumption pulls the ground out from beneath the entire framework. This brings us to the second way that physics breaks at the Planck scale, and it is even more conceptually disturbing than the infinity problem. It has to do with what quantum mechanics does to space-time itself. In quantum mechanics, every field fluctuates. Even in a perfect vacuum at a temperature of absolute zero, with not a single particle present, quantum fields are never perfectly still. They vibrate and fluctuate due to the uncertainty principle. You cannot simultaneously fix a field's value and its rate of change to 0. There is always a residual jittering, called vacuum fluctuations or zero-point fluctuations. These fluctuations are real and measurable. They produce the Casimir effect, a tiny but detectable force between two closely spaced metal plates in a vacuum. They produce the Lamb shift, a subtle change in the energy levels of hydrogen that has been measured with extraordinary precision. Vacuum fluctuations are not theoretical speculation, they are confirmed experimental facts. Now, in general relativity, the gravitational field is space-time geometry. The curvature of space-time is determined by the energy present in a region. Energy of any kind, including the energy of quantum vacuum fluctuations, curves space-time. At large scales, the energy of vacuum fluctuations is distributed so smoothly and uniformly that it produces no detectable effect on space-time geometry. The fluctuations average out over macroscopic distances. Space-time remains smooth and well-behaved, exactly as Einstein described it. But at very small scales, the fluctuations do not average out. The uncertainty principle guarantees that at smaller length scales, the energy fluctuations become more violent. The smaller the region you examine, and the shorter the time interval you consider, the larger the energy that can temporarily appear and disappear. This is a direct consequence of the energy-time uncertainty relation. For extremely short time intervals, the uncertainty in energy becomes extremely large. Enormous amounts of energy can briefly materialize from the vacuum, as long as they vanish quickly enough. At the Planck scale, these energy fluctuations become so enormous that they curve spacetime dramatically. The fluctuations are violent enough to warp and deform the geometry of spacetime on the scale of the Planck length. Spacetime at this scale would not be a smooth, gently curving fabric. It would be a wild, frothing, chaotic mess. Tiny black holes would spontaneously form and evaporate in intervals of 1 Planck time, roughly 10 to the negative 43 seconds. Wormhole-like connections between distant points would flicker into existence and vanish. The topology of space, the fundamental way that regions are connected to each other, would fluctuate wildly. One instant, 2 points would be separated. The next instant, a wormhole would connect them. Then it would collapse, and they would be separated again. John Archibald Wheeler, one of the most important physicists of the 20th century, coined the term space-time foam to describe this picture. He imagined space-time at the Planck scale as something like a turbulent ocean viewed at the molecular level, all froth and chaos, with no smooth surface in sight. From far away, from the perspective of atoms and particles and planets and galaxies, space-time looks perfectly smooth, just as the surface of the ocean looks smooth from an aeroplane. But zoom in far enough, and the smoothness gives way to violent quantum turbulence. And here is the devastating implication. If space-time is foaming and fluctuating at the Planck scale, then the very concepts we use to describe geometry lose their meaning there. Distance becomes undefined. How do you measure the distance between 2 points if the space between them is constantly shifting, bubbling with quantum black holes and wormholes? Curvature becomes undefined. How do you describe the curvature of spacetime if the geometry is fluctuating faster than you can characterize it? Even the number of dimensions might fluctuate. Some theoretical frameworks suggest that the effective dimensionality of spacetime changes at the Planck scale, that at the very smallest scales, spacetime might behave as though it has fewer than 3 spatial dimensions. General relativity is a theory of geometry. It describes the curvature of spacetime, the distances between points, the angles of geodesics, the topology of space.
Every concept in general relativity presupposes that spacetime has a well-defined geometry. But at the Planck scale, quantum fluctuations destroy that well-defined geometry. The subject matter of general relativity, smooth spacetime geometry, ceases to exist in the usual sense. This is not like saying a theory becomes less accurate at extreme conditions. It is saying the very thing the theory describes may not exist in a recognizable form at those conditions. It would be like trying to use fluid dynamics to describe the behavior of water at a scale where individual molecules are visible, and the concept of a continuous fluid has broken down completely. The third way the conflict manifests is through a specific, concrete puzzle that has tormented physicists for half a century. It is called the black hole information paradox, and it demonstrates the conflict between quantum mechanics and general relativity in a way that is both vivid and precise. In 1974, Stephen Hawking made a remarkable discovery. Using a careful calculation that combined quantum field theory with the curved spacetime of general relativity, he showed that black holes are not perfectly black. They emit radiation. A black hole has a temperature, and it glows, radiating energy in the form of particles that stream away from the event horizon. This is called Hawking radiation, and it is one of the most important results in theoretical physics of the past century. The mechanism is rooted in quantum vacuum fluctuations near the event horizon. In the vacuum, pairs of virtual particles constantly pop into existence and annihilate each other almost immediately. Near the event horizon of a black hole, something unusual can happen. One particle of the pair falls into the black hole while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. The infalling particle, from the perspective of an outside observer, effectively carries negative energy into the black hole, reducing its mass. Over time, the black hole loses mass through this process. It shrinks. It gets hotter as it shrinks, and it radiates faster. Eventually, after an extraordinarily long time for any black hole of astronomical size, the black hole evaporates completely, disappearing in a final burst of radiation. This raises a deeply troubling question. Quantum mechanics has a fundamental principle called unitarity. It states that information is never destroyed. The quantum state of a system at any time contains all the information needed to reconstruct the quantum state at any earlier time. The evolution of quantum states is reversible. If you know the final state of a system perfectly, you can, in principle, reconstruct the initial state. Information is always preserved, even if it becomes scrambled and difficult to access in practice. Now consider what happens when something falls into a black hole, and the black hole subsequently evaporates. An object falls in carrying specific quantum information about its state, what type of particle it was, its exact quantum configuration, its correlations with other systems. The black hole then evaporates via Hawking radiation, but Hawking's calculations showed that the radiation is thermal. It is essentially random, like the radiation from a hot piece of metal. It carries no information about what fell into the black hole. The radiation depends only on the black hole's mass, charge, and angular momentum, nothing else. Every black hole with the same mass, charge, and spin emits the same Hawking radiation, regardless of what formed it, regardless of what fell into it over its lifetime. So where did the information go? It fell into the black hole. The black hole evaporated. The radiation carries no information. The information appears to have been destroyed. But quantum mechanics says information cannot be destroyed. This is a direct contradiction between quantum mechanics and general relativity. Quantum mechanics demands that information is preserved. General relativity, combined with quantum field theory in curved spacetime, predicts that it is not. This is not a minor puzzle. It strikes at the foundations of quantum mechanics. If information can be destroyed, the entire framework of quantum theory becomes inconsistent. Probabilities would no longer add up to 1. The past would not be determinable from the future, even in principle. The mathematical structure of quantum mechanics would collapse. Some physicists initially sided with Hawking and accepted that information is lost. This would mean quantum mechanics needs to be modified in the presence of strong gravity. Others insisted that information must somehow escape, encoded in subtle correlations in the Hawking radiation, that Hawking's original calculation was too crude to capture. This was the position most famously championed by Leonard Susskind and others. The debate raged for decades, and in many ways it continues today, though the consensus has shifted toward the position that information is preserved and that our understanding of what happens at the event horizon, and possibly the very nature of spacetime, must be revised. The information paradox is not an isolated problem. It is a symptom of the deeper incompatibility between quantum mechanics and gravity. It arises precisely because we are forced to apply both theories simultaneously in a regime where both matter, the quantum behavior of fields near an event horizon, combined with the extreme spacetime curvature of a black hole. And when we do this, we get a contradiction. The resolution, whatever it ultimately turns out to be, will require new physics. It will require a framework that goes beyond both quantum field theory on a fixed background and classical general relativity. The fourth manifestation of the breakdown is the problem of singularities. General relativity predicts that under certain conditions, spacetime curvature becomes infinite. This happens at the center of a black hole, where all the infalling matter collapses to a point of infinite density. And it happens at the very beginning of the universe, in the standard Big Bang cosmology, where extrapolating backward in time leads to a state of infinite temperature, infinite density, and infinite curvature. These singularities are not physical predictions. They are not telling us that nature actually produces infinite densities or infinite curvatures. Infinity is not a number you measure in a laboratory. A singularity in a theory is a signal that the theory has been pushed beyond its domain of validity. It is like pressing the accelerator of a car to the floor and watching the speedometer needle swing past the maximum and slam against the pin. The pin does not tell you the car's actual speed. It tells you the speedometer cannot handle what is happening. Similarly, the singularities in general relativity do not tell us what actually happens at the center of a black hole or at the first instant of the universe. They tell us that general relativity cannot handle what is happening there. Something else takes over. Some other physics governs the behavior of matter and spacetime at those extreme conditions. And we know what that something else must involve. At a singularity, matter is compressed to densities far exceeding the Planck density. Distances shrink far below the Planck length. Curvatures reach scales where quantum effects cannot possibly be ignored. The singularity is exactly the kind of regime where quantum mechanics and gravity are both essential, where both must be accounted for simultaneously. And since we lack a consistent framework that does this, the singularity remains a blank spot in our understanding. We know general relativity breaks down there. We strongly expect quantum effects resolve the singularity somehow, replacing the infinite values with finite ones. But we cannot yet calculate what those finite values are, because we do not have the complete theory. Inside a black hole, most researchers expect that quantum gravity effects prevent the matter from collapsing to a true point of infinite density. Something happens at the Planck scale that halts the collapse. Perhaps matter bounces. Perhaps it reaches a state of maximum density determined by the Planck density and cannot compress further. Perhaps the very concept of a spatial point breaks down, and the singularity is replaced by a region of fundamentally quantum spacetime where classical geometry does not apply. But without a complete theory of quantum gravity, we are speculating. Educated speculating, guided by the principles of both quantum mechanics and general relativity, but speculating nonetheless. At the Big Bang, the situation is similar but even more consequential. We already know that the entire observable universe was once compressed to a size smaller than a Planck length, with temperatures and densities that place every point squarely in the quantum gravity regime. But the singularity problem adds a sharper edge. General relativity does not merely struggle to describe this epoch. It predicts that extrapolating backward leads to a moment of genuinely infinite density and curvature. Infinite. Not merely large, but mathematically unbounded. That prediction is almost certainly not what actually happened. It is the theory crying out that it has been pushed past its breaking point. Whatever replaced that singularity, whatever actually occurred in the first moment, required physics that encompasses both quantum mechanics and gravity simultaneously. The very origin of the universe, the most fundamental question about why anything exists at all, is locked behind the Planck scale. These are not four separate, unrelated problems. The non-renormalizability of gravity, the spacetime foam, the black hole information paradox, and the singularities are all symptoms of the same underlying disease. They are all consequences of the fact that we do not have a single, consistent framework that incorporates both quantum mechanics and gravity. Each problem appears when we are forced to apply both theories simultaneously. Each one produces contradictions, infinities, or meaningless results. And each one points to the same conclusion. Something fundamental is missing from our understanding of nature. Every major revolution in physics has begun exactly this way. A proven framework encounters a regime where it produces contradictions or nonsensical predictions. The contradictions persist for years or decades, resisting every clever workaround, until someone discovers a deeper theory that resolves them. The old theory is never discarded. It continues to work perfectly in its original domain, but the new theory reveals it as an approximation of something more fundamental, a theory that was hiding just beneath the surface all along, waiting for the right contradiction to force it into view. The incompatibility between quantum mechanics and general relativity has exactly this character. It is the signal that our current theories, magnificent as they are incomplete. Something fundamental is missing, something that only becomes apparent at the Planck scale, where quantum effects and gravitational effects collide. And whatever that missing piece turns out to be, finding it will not merely fix a technical problem. It will transform our understanding of space, time, matter, and the nature of reality itself. The question then is what comes next? What does it mean to say physics breaks? And what would a resolution look like? What are physicists actually doing about this problem? And what hope do we have of solving it? Because the story does not end with the diagnosis. The breakdown of our theories at the Planck scale is not a dead end. It is a signpost pointing toward the next great revolution in our understanding of the universe.